We are talking about both exponential growth and decay in lesson 10.6. So we are just going to look at exponential growth problems in this video. How can exponential growth be used to predict future sales? The graph shows the average household in the United States has increased its spending for restaurant meals. In fact, the amount grew at an annual rate of about 4.6% between 1994 and 1998. If we let y represent the average amount spent on restaurant meals and let t represent the number of years since 1994, then the average amount spent on restaurant meals can be modeled by y equals 1698 times 1 plus 0.046 to the t, or y equals 1698 times 1.046 to the t. Typing the equation that they gave us into GeoGebra lets us see how the curve increases more steeply the further it gets from zero. The equation for the average amount spent on restaurant meals is in the form y equals c times 1 plus r to the t. This is a general equation for exponential growth, in which the amount c increases by the same percent over a given period of time. In 2000, the United States had a population of about 280 million and a growth rate of about 0.85% per year. Write an equation to represent the population of the United States since the year 2000. C stands for what we started with. So they said the original population was 280 million, and they were growing by 0.85%. So as a decimal, when we change a percent to a decimal, we have to move our decimal 2 places and to the t. So just adding 1 plus 0.0085, we've combined it down to an equation we can work with. According to the equation, what will the population of the United States be in the year 2010? So we're going to put 10, because it was years since 2000, and type it in the calculator. And I got 304,731,295. When I Googled it, it was actually 309.3 million. So that's, ballpark prediction as predicting into time not past goes. For future reference, that's called an extrapolation. We're looking into the future. Interpolations tend to be much more accurate when we're looking into the past, and we could interpret something that's already gone on back here. Out here, could keep doing the same thing, could not. It's hard to say. One special application of exponential growth is compound interest. The equation for compound interest is A equals P times 1 plus R over N to the NT, where A represents the amount of the investment, P is the principal, initial amount of the investment, R represents the annual rate of interest expressed as a decimal, N represents the number of times that interest is compounded each year, and T represents the number of years that the money is invested. When Jing Mei was born, her grandparents invested $1,000 in a fixed-rate savings account at a rate of 7% compounded annually. The money will go to Jing Mei when she turns 18 to help pay for her college expenses. What amount of money will Jing Mei receive from the investment? The principal is the amount that it was invested, so that's $1,000. The formula always has a 1 plus R is the rate as a decimal, so 7%, 0.07, over it's compounded annually, so that's just going to be a 1, and then to the, and we said was 1, and this is going to go on for 18 years. So the amount that she'll receive will be $3,379.93, rounding to the nearest penny, which makes sense with money. Well, we've done 2 parts of the whole lesson. Exponential growth is y equals c times 1 plus r to the t, where y represents the final amount, c represents the initial amount, r represents the rate of change expressed as a decimal, and t represents time. Compound interest is a special case of exponential growth, where a equals p times 1 plus r over n to the nt, where a represents the amount of investment, P represents the principal, R represents the annual rate of interest expressed as a decimal, N represents the number of times that the interest is compounded each year, and T represents the number of years the money is invested.